Okay, it is now started recording. Good evening, everyone. Welcome to this tutorial class. It is now 5 minutes past 6. We'll have our tutorial class. So I will start by looking at the first problem in assignment 1. That's what I'm going to look at. Is one of the first thing we learned when we defined organic chemistry. We saw that organic chemistry is the study of the chemistry of carbon compounds, and then the number of organic compounds that are available is very, very many. And then as a result, if it goes with that, the study of organic chemistry should be very difficult. But the study of organic chemistry is made easy because of the fact that what determines the properties, physical properties, chemical properties, or even biological properties of an organic compound is the functional group. So as a result, it is very important as we are starting to study organic chemistry, we must first understand the different functional groups. When you look at a functional group, you must recognize it. You remember when we studied about the intramolecular and intermolecular force of attraction, we talked about hydrogen bonding, we talked about dipole-dipole interaction. Whether a particular molecule is going to have dipole-dipole interaction or hydrogen bonding, etc., will depend on its functional group. So very important that we understand what functional groups are and what are the different types of functional group. So in this particular molecule, this is the last problem from the first assignment, the first question from assignment 1, to locate and identify the functional group in the following molecules. That's what it says, but I have identified this one. And then as you can see, this one will give a very good representation of all the other questions we are asked to locate their functional groups for. So as you can see, this molecule is a multi-functional group molecule, an organic compound that has got several functional groups. And this is indeed the case for many important organic molecules. They have several functional groups, each of which play a very important in the property of the molecule. So what I'm going to do now is first we'll just identify the simple ones, okay? First we identify the simple one, the easy one, the ones we know, and then we build on that. So the first one you can easily identify is that you have in here, you have a carbon-carbon double bond, isn't it? What is this functional group?
Alkene.
This one is alkene.
Alkene.
Yes. And then we have this carbon-carbon triple bond. This carbon-carbon triple bond is?
Alkyne.
Okay, alkyne. So these are the easy picks. And then when you look at this molecule, it has got, how about this one? First, let me first look at this one. What do you call this one?
Amine.
Okay. How about this one? This one, we have an oxygen.
Ether.
Then on both sides of the oxygen, there is carbon. This one is an ether, okay? So. Now, the rest of them have carbon-oxygen double bond, carbon-oxygen double bond, carbon-oxygen double bond, carbon-oxygen double bond, carbon-oxygen double bond. So molecules that have carbon-oxygen double bond like this, let me discuss with you in a simple way, okay? Let me discuss with you in a simple way that we have different types of carbonyl compounds, okay? We have different types of carbonyl compounds. Carbonyl compounds. And these are compounds that have a carbon-oxygen double bond, okay? Such compounds are called carbonyl compounds. So on this side, you can have an R, whatever R is. And then on this side, we have a Z. Okay? R can be carbon, R can be hydrogen. Okay? So now, when R, okay, R. So when you have Z, when Z is a hydrogen, what do you call this carbonyl compound when Z is a hydrogen? It will be
Carboxylic acid.
No, when Z is a hydrogen, it is an aldehyde.
Aldehyde.
When Z is a carbon, when Z is a carbon, it is aldehyde. When Z is a carbon, it is
Ketone.
When Z is OH, it is carboxylic acid. When Z is O, R, to make it different, let me call it R prime, it becomes an ester. When Z is equal to nitrogen, and then to this nitrogen, we have two different R groups. Let me call them R1 and R2. This one is called amide. And then when Z is chlorine, this one is called acid chloride, acid, or acyl chloride, okay? So, for you to determine what type of carbonyl it is, it could be an aldehyde, ketone, carboxylic acid, ester, amide, or acid chloride. You have to look at the groups that are attached to the carbonyl. If on one side of the carbonyl, you have a hydrogen, it's an aldehyde. If it is on both sides, if it's a carbon, on both sides, if it's a carbon, it's a ketone. If the carbonyl is attached to an OH, it is a carboxylic acid. If it is attached to an OR instead of an OH, or for example, CH3, that one is an ester. And then, but when Z is a nitrogen to which two alkyl groups are attached, it is an amide. However, when Z is chlorine, it is an acid chloride. So based on this, when you come here, you have this carbonyl, okay? What do you call this one? Hello?
Aldehyde.
You cannot fail to recognize this, okay? It is an aldehyde. And then, if you look at this one.
Excuse me, sir, please
Yes,
reshare your screen.
Reshare.
Yes. Yes.
Okay, again. Okay, let me reshare. Hello? If your place is very noisy, please do not unmute, okay? How about now?
Thank
Can
you.
you
I can
see?
see.
Okay. What do you call this one? This one.
Keton. Keton.
Because we have a carbon oxygen double bond on both sides, we have a carbon. So this one is a ketone.
Keton.
Okay. And then when you look at this one, we have a carbon oxygen double bond attached to an OH. This one is
Carboxylic acid.
Carboxylic acid.
and then when you look at this one, this one is
Esters.
and then the last one, this one. This one is
Amide.
amide. Okay, so all you need to do, learn these functional groups by heart. And then one of the mistake I see students make is like, for example, this one is a carboxylic acid. They will identify the OH, they will put the OH, they will circle the OH, tell me it is an alcohol. And then they will circle the carbon oxygen double bond and then they say a ketone. But what makes this a carboxylic acid is that we have the fact that you have a carbon oxygen double bond, and then to the carbonyl carbon we have an OH directly attached. That is a carbon. So this is one unit. The same is to this. It is amide, carbon double bond oxygen together with a nitrogen. This one is an amide. You cannot say ketone and amine. An amine is where you have a nitrogen directly connected to a carbon, and then that carbon is connected to another carbon like that. Okay, but not this one. We have a nitrogen that's connected to a carbon, then that carbon is bonded to through a double bond. This one is an amide. Okay, is it clear?
Yes.
Yes.
Now,
Yes.
let me give. So I really do not have to go through the others. What I want you to do.
Excuse me, sir.
Yes, yes.
I have a question.
Yes.
When Z is N, you say this.
When Z is
N.
N, yes. When Z is a nitrogen,
We say
it is an amide.
Amide.
Okay. Yes, you see, when Z is N, nitrogen, that's a type 2 alkyl group, it is amide. Okay?
Thank you. Yes.
Yes. Okay. So let me look at one problem. This one. This one is on electronic configuration. So it says write the electron configuration of the following elements by abbreviating their configuration to the nearest noble gas and draw an orbital filling diagram indicating the electrons as up or downs. So let me first look at the electron configuration of the element with an atomic number of 29. Z is equal to 29. So when you are writing the electron configuration, you are arranging these 29 electrons in terms of the shells, their subshells, and the orbitals. You allocate these 29 electrons in shells, subshells, and orbitals. So as I've told you, when you are writing the electron configuration, you don't need to cram. Just know that the known element in the periodic table, they lie in 7 shells. 1, 2, 3, 4, 5, 6. We have 7 shells. So in the first shell, we have the S subshell. In the S subshell, there is only one orbital, and that orbital carries 2 electrons. So this S subshell exists in all the different shells. So we have S here with 2 electrons, S here, S here, in all the shells, except what makes the S in the first shell different from the S in the second, in the 7th shell, for example, is that the S in the first shell is 1s2, while the S in the 7th shell is 7s2. Then in the second shell, in addition to the S, we have P, and then P carries a maximum of 6 electrons. So 2 plus 6, 8. The 8 electrons of the second shell are found in the S subshell and the P subshell. When you go to the third shell, we also have P. Then we also have P in all the others. Okay, P6, 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 P6. Okay. Then in the third shell, in addition to the S and the P subshells, we have the D, and the D carries 10. So that's why 2 plus 6, 10, and 2 plus 6, 8, 8 plus 10, 18, the maximum number of electrons in the third shell. So all the other shell will also have D.
Excuse me, teacher. The screen
Yes.
we can see is about the ketone and the aldehyde. You have not changed the screen.
I have changed. It is you who got stuck in there. How about the rest of you? Can you see it?
Yes.
Yeah, we can see.
I can see now.
So let me reshare. Let me reshare. You know, it's just because of bad connection that you can get stuck. I don't know if you can see it now.
Yeah, I can.
So in the F, in the third shell, we only have S, P, and D. From the fourth shell, we have F. Okay, so F14, F14. So you can write the ground state electronic the configuration of all the known elements using these shells, subshells, and orbitals. So first you fill the S, after 1s2, then 2s2, then 2p6, then 3s2, and then like that. You just follow this arrow, nothing else. You don't create your own funny things, okay? You just follow these arrows. Okay? The last shell to be filled will be the 7f42. So now, so this is how we do it. You fill the first cell, after that you go to fill this one. When this one is done, you go up here. When this one is done, you go here. When this one is done, you come up here. So you just follow the arrows. Okay? Like that. So let's quickly do for Z is equal to 29, okay? We'll count and follow this until we reach 29, okay? So 1s2. After 1s2 it is 2s2.
2p6.
After that it is 2p6. After 2p6 it is 3s2.
3s.
After 3s2 is
3s.
3p6.
after 3p6 it is
4s1.
4s2. Let's just say, let's go straight for s2, and then
3d10.
3d
10.
9. Now you see 2 plus 2 up to here it is 10, isn't
9.
it? 2 plus 6, 10, 10 plus 2, another 10 here. So these are 29 electrons in total, okay? 29.
17, 18, 19, 25, 26, 27, 29.
29 electrons, isn't it?
Mm.
So when you look at this, the 3D9, this one, in order to have a complete orbital, because you remember the D subshell carries a maximum of 10 electrons. In order to have a complete shell, it only needs 1 electron. So what we're going to do, we just say half filled, and fully filled. D orbitals are stable. Half filled and fully filled. The orbitals are stable. As a result, we can promote one of the electrons from the 4s2 and take it to, so let me just copy this one. Let me copy this. Who is driving today? Now, so what we'll do, we'll promote one of the electrons from the 4s1, from the 4s2, we give it to the 3D so that we have a 3D10, which is a completely filled d orbital. Therefore, the electron configuration of the electronic configuration of the element with Z is equal to 29 is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10. Okay? And then when you abbreviate this, you will see that this is the electronic configuration of argon, the nearest noble gas. So this will be represented by square bracket argon, okay? Ar. So what you will be left with will be 4s1, 3d10. So this is the abbreviated electron configuration for the element with Z is equal to 29. Then when you fill the orbitals, we keep the AR the way it is. So S, it is just one orbital. So you have one electron in here. And then the D are 5 orbitals. In the D subshell, we have 5 orbitals. So you take one space and split it into 5. Take the D subshell and split it into 5. So we have 10 electrons. We fill 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So this is how you write the electron configuration of the element with Z is equal to 29. Okay. So I have, I know Ahmed, you are not telling me, but it is almost 6:29. I will allow some of our Muslim brothers and sisters to go and have a prayer for about 10 minutes. You guys, okay? You go and pray for 10 minutes and you come back. We'll have just a small discussion with the rest of the class as we wait for you. Ikosawa?
Yes, I was about to tell you that.
Okay, good.
Yes.
Yes. And so the rest of you, have you understood what I talked about?
Yes, but I have a question.
Yes, Samuel.
What about the commas? I saw we used it in SH11.
What did you, how did you do it?
We were putting commas at every, like one
Oh,
is 2, comma.
2 is 2, comma, like that.
Yeah.
Oh,
Me, I really don't mind if you put them is okay, but it's really not necessary for me. And one of the things I want you also to see that me, I'm an organic chemist, okay? An organic chemist.
Yeah.
I deal with the chemistry of carbon compounds, and as a result, inorganic is not my thing. Dr. Madadi is a specialist in organic chemistry, which is even electronic configuration, etc. Because he talked about quantum numbers, isn't it? Me, I do not talk about those. So it is possible you can follow the way he's done it. Yeah, but for me, it is very important that at least you know the shells, subshells, and orbitals in which electrons are found. Because at the end of the day, it is this arrangement of electrons, particularly the valence electrons, which is going to tell us, first of all, whether the bonding is going to be covalent or ionic, and also if they are covalent, what electrons in which orbitals are they going to overlap when that covalent bond is formed, okay? So I'm interested in you knowing the different orbitals that are there in the valence shell, the ones that are going to overlap to give us the covalent bond, okay? So that's what my focus is mainly, okay? So if you are told we should put comma by Dr. Madadi, and that is the norm, it is very well and good, okay? That's all. Any other question? Which question from the assignment disturbed you most? Which area?
Resonance.
Resonance structure, drawing
Resonance structures, isn't it? Yes.
Yes, also hybridization.
And also hybridization. Okay, no problem. I know hybridization is not very complicated, but we'll deal with it. But resonance might be challenging, but we'll talk about it, and I will take my time and explain. And because I believe it is one of the most important concepts you have to know in order to understand organic chemistry. I can assure you, even in your research life, after you have finished your PhD, you will still be using the concept of resonance in explaining some things. Even in seeing how drugs work, many things. Okay, so it's very important you have a clear understanding of chemistry. I mean resonance. So before we reach the stage of resonance, we'll first look at how to draw Lewis structures, and then as we do that, then we'll see why the structure of some compounds cannot be represented by a single structure, why we need to draw resonance, and then the stability of the different resonance contributors. Why is one particular resonance contributor more stable than the other one? You can even look at two different compounds that are resonance stabilized, And then you can compare and look at the different resonance of these compounds and decide and determine which one of them is very stable. You know, what I want you to see is like this. Which family is in a position to handle financial crisis? Or, for example, if a bill comes to that family because of a family member being sick and a very big hospital bill comes. And of course, you know, our financial situations are not the same. And in Kenya, we have the spirit of Harambee, and a family that has network, a big family with many siblings, aunties and uncles, with many big extended family, can easily handle this financial burden compared to a family that does not have network. So when you talk of resonance, resonance brings stability because suppose you have a positive charge. And this positive charge is a problem. It is because of that positive charge, the molecule is unstable. Because it is very difficult to have a positive charge, which is deficiency of electrons, or excess of negative charge, which is excess of electrons. And then because of this, because of deficiency or excess, molecules become unstable. They would love to have the right number of electrons, the octet number of electrons, then they become stable. So having a positive charge or having a negative charge makes a molecule unstable. Now, it just depends on how this positive charge, which is the burden, how is the positive or the negative charge is shared by the neighboring atoms. If the positive or the negative charge can be shared by many atoms, it can spread out. Rather than the positive charge being on that particular atom, it is shared by all the other neighboring atoms. So when a molecule has got many resonance, it has got many ways of delocalizing or distributing the positive charge. So this is like a family that has got big network that can easily take the burden of the family. See, like when you have 1 million shilling to raise, whether if people come to solve that problem through Harambee, the problem does not go. The problem still remains at the end of the day that 1 million shilling has to be raised. It is there. What makes it easy for the family is the fact that so many people have taken the burden. So that 1 million shilling, one family take the burden of 10,000 shilling, another one 5,000 shillings, another one 500 shilling, like that. The burden, the problem is spread out, it's shared. So since the problem is shared, it did not disappear, it was shared. So, but the burden on that particular family became easy. So when you have a positive charge or a negative charge on an atom, it's like you need some money that you have to raise, like 1 million shilling, a problem that you have to solve. But if the carbon atom has got many other neighboring carbon atoms or other atoms that can share through resonance that positive or that negative charge, it becomes stable, it becomes very easy compared to one that has got few number of resonances. So I will discuss with you with examples. The examples we have are in the assignment are quite adequate. And then those ones or any other question you have related to resonance, you bring it. We have a discussion on it so that the concept becomes very clear to all of us. Okay? I'm personally, I'm telling you, even if you call me on Christmas Day, let's have a discussion. I will be available. So all I'm trying to say is I will be there for you to explain to you whatever problem you have. I'm willing, okay? Whatever problem, so that at the end of the day, everything becomes clear. Okay, so we'll wait kidogo a bit more for King Ahmed to finish the prayer and come. Okay, Faith, you have a question? Or oh,
Excuse me, sir, I have a question.
yes. Yes, Kerubo.
Okay. Yes, I was asking about the arrangement of the electrons.
Mhm.
Can you place the 4s just after the 3d10?
Yes, you know, it is possible because there are so many, even in the periodic table I have prepared. Even in the periodic table I have prepared, that's how I did it, okay? But what you should know, the order in which they are filled is the 3D before the 4S, okay? That's all. We should not forget that. Otherwise, it is possible. It is possible
Yes.
you can put them like that for the sake of it. But we should not forget. And I don't want you to think that the 3D is filled before the 4S. You cannot, for example, if you have 2 electrons, you cannot put those 2 electrons on the 3 as 3d2 and leave the 4s empty, okay? Those 2 electrons must go to the 4s2. It is only after the 4s2 is filled, now you go to fill the 3d10, okay? The 3ds. Isn't it true? Yes.
Yes.
Yes. I personally would like to put them the way this sequence telling me. I would put 4S and then 3D10. But if you put it the other way, I also understand. But so long as you don't feel the 3D before the 4S. We'll wait for 1 or 2 minutes, okay? Sorry. Nancy, you have a question?
Yeah, I've got a question, sir.
Mm-hmm.
I wanted to ask, like, I want to write the electronic configuration of a certain element.
Mm-hmm.
And then, like, I've not been told to write to the nearest noble gas.
Mm-hmm.
Yeah, despite it, I write it. Is it an offense to do so?
No, my dear. If you, for example, if you go over and above, there's no punishment, isn't it?
Yeah.
But it is only a punishment will come in. For example, in this particular case, you are told to write the electron configuration, elevate it to the nearest noble gas, and then write the electrons as up and downs when filling the orbitals. If you fail to do that, you'll be punished. But if I just ask you write the electron configuration of the element with z is equal to 29, then you write it as 4s1 3d9. That's where you should stop. But you have gone further ahead, abbreviated it, and done extra work. If there was any bonus point, I would have given you. Okay, there's nothing wrong you
Yeah.
have done, Senior.
Yes.
Yeah.
Thank you. I don't know if Kina Ahmed are back. Let's just give them 1 more minute, okay?
Yes.
Yes,
Okay.
just give them 1 more
Sir,
minute.
I have a question.
Yes.
Yeah. For example, if you're told to write an electron configuration of an element, the atomic number maybe, okay, let's say that when by writing the electronic configuration, you find that the D does not reach, is not, maybe it is D3, But then it is said that while writing the electronic configuration to the nearest noble gas, the D should be half or fully filled. So if it is D3 and then we have 4s2, so how are we going? Are we going to remove all the two to make the D be half filled, or we're just going to remove one?
You are going to. It is safe. It is better. Like you remove the one electron from the 4s1 and put it from the 4s, put it in 3D. Okay?
Yeah. Yes.
Like that. I'm trying to look at for some examples. You have my periodic table.
Yep.
Do you have the periodic table I shared?
It is in the notes. I don't have it.
There's a whole Kiswahili English periodic table I shared. And then this Kiswahili English periodic table, it has got the abbreviated electronic configuration of all the elements. You did not see it, Felix?
Yes.
You did not see it?
Let me just open it.
Okay, anyway. Ahmed, are you back?
Yes, you're back.
Okay, good. Thank you so much. So you have not missed much. We are just chatting, okay? And so what I want to do next.
Excuse me, sir.
Yes.
I'm requesting that you show the slide whereby you are identifying the functional group so that I may screenshot.
You see, you thought I'm a dictator. Me, if you had asked me, you only need to say is share this thing after I will share it with you, the recording, even the slides, these slides, okay?
Yes.
So did you manage to screenshot this one?
No, wait. Oh.
Done?
Not this one. Not this one. Whereby you are writing Z is equals to
this
carboxylic acid. That one.
This one?
Not. Yeah, this one. Thank you.
Thank you. So now we looked at for Z is equal to 29. Now let's write the electron configuration for Z is equal to 47. Then we rest this discussion on electronic configuration, okay? So we'll do for Z is equal to 47. Now, what the usual thing to do, I don't want you to cram anything, okay? And I want you to quickly write this, okay? This, and then the arrows, which you do not have to cram. You develop this so that you can easily follow up. So now let's do this. So we're going to follow this arrow until we reach 47, okay? So we have 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2, 3d10. Now I want us to count. This is 10, another 10, another 10. We have reached 30, okay? So 3d10. After 3d10, it is after 3d10 is 4p6. After 4p6, it is 5s2. So, and after that is 4d. We have to count, okay? So this is 10, 20, 30. Oh, this should be 9, isn't it?
Yes. Yes, there should be 9.
So of course we'll promote one of the electrons to the other side, so it will be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s1, 4d10. Now, if you look at the element with an atomic number of 47 in the periodic table, so you must have, when you want to abbreviate, you must have the periodic table with you. Okay, and then the element with the atomic number of 47 is silver, but the noble gas just before silver is which is the noble gas just before silver?
Okay.
The noble gas just before silver is krypton, okay? And all the way here, this one, this, if we count, 2 plus 2, 4, 4 plus 6, 10, 12, 12 plus 6, 18, 18 plus 2, 20, 20 plus 10, 30, 30 plus 6, 36. This one is nothing but krypton, okay? So you will abbreviate that one as Kr. Then 5s1, 4d10. Okay, so when you abbreviate, of course, it will be Kr. Then you have the S. In the S subshell, we only have one orbital, and then that one has got one electron. In the D subshell, we have 5 orbitals. So the 5 orbitals, they are all in the D subshell. So you are going to just partition that one into 5. 1, 2, 3, 4, 5. Do not do it like this. I don't want you to do it like this. Not like this, okay? This one is like they are they are different subshells. So they are the same subshell. So this is the D subshell is a subshell that has got 5 partitions, 5 orbitals of equal energy that carry the same, 2 electrons each. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, this is how you write the electron configuration. Is it okay? Are you guys okay?
Yes.
Yes.
Okay.
Okay.
It's okay.
Now,
Excuse me, I
yes,
have a
yes.
question.
Yes, please ask.
I was asking, for instance, the one that you finished with, you've gone 4p6, then 5. It was 5s1 and then 4d10. Should you fill the 5s orbital before filling the 4d orbital?
Yes.
Huh? Yes. For example, if we do not have any, for example, if the atomic number was, for example, 37, if it was 37, we'll stop at 5s1 If it was 32, we'll go to 5s2. Now, if it was the next number after 5s2, we'll go to 41. Okay? So that's how we do it. Is it okay? Okay, Rubo,
Yeah. Yeah,
you're
it's
okay? Good, thank
Yeah.
you. Now, we are going to do another example. We're going to look at the other question. This time is on writing Lewis structure. Okay. So I have identified the ones in red for our discussion. Okay. Okay. Let me add this one. Okay. Let me add also this one. Okay. I will discuss these ones as time allows. Okay. Okay, so first, let's draw the Lewis structure for NH2OH, okay?
Okay, sir, I
Yes.
have a question back there while we were writing the electronic configuration.
Yes.
So, for example, I've gotten an element in the 8B group 8B, and that is element now atomic number 46. So, if we are told to write the electronic configuration to the nearest noble gas, I think the D is going to be having 8 electrons, and it is said that it should be either half fully filled,
Which element did we say?
Let me see, an element in group 8B. That is I don't know, it's abbreviated PD.
Palladium.
Yeah, palladium, that one. So if we are told to write the electronic configuration to the nearest noble gas, are we going to empty all the 5s, or we're just going to remove one electron?
Because that one will not have any electrons.
Yeah.
Because the element just before this, isn't it?
Yeah.
The element just before this. It will be 4d10 according to this. So it will not have any. It will not have any electrons in the 5s.
Yeah.
Okay. So it will be krypton, and then 4d10. Okay.
Yes.
Yes. So let me look at this Lewis structure, drawing of Lewis structure. So let me start first by looking at this.
Excuse me, sir.
Yes, yes.
So by writing, after borrowing the electrons, the electrons in S orbital to the 4D. So you just omit the 5s.
Yes, yes. It will be an empty shell.
Okay, thank you.
Okay. So when drawing Lewis structure, I told you we follow steps, isn't it? So we follow steps. Is this pen drawing, is it visible?
Yes.
Or do I change the color?
Yes, it is visible.
Eh?
It is visible.
Okay.
visible.
It is visible.
So steps in drawing Lewis structure, okay? So the first step, number 1, it says arrange the atoms, okay? Arrange the atoms. So when you are arranging the atoms, of course, we are following some basic concepts. One of the things we know that hydrogen forms only one bond. Therefore, hydrogen cannot be in the middle. It cannot be at the center. Hydrogen can only be in the outside. 1. 2. When you are surrounding either carbon, nitrogen, oxygen, etc., as the first approximation, we should not surround them by more than the number of atoms. You should not surround them by atoms more than the number of bonds they usually form. For example, nitrogen forms 3 bonds, as in the case of ammonia. So when you are surrounding the nitrogen by other atoms, okay, as a first approximation, you should not surround the nitrogen by more than 3 atoms. If it is an oxygen, oxygen is divalent. Oxygen forms 2 bonds, as in the case of water. So as a first approximation, you should not surround oxygen by more than 2 atoms. If they are halogens like chlorine, etc., as in the case of HCl, fluorine, as in the case of HF, the halogens form only 1 bond. So just like the hydrogen, the halogen should be on the outside. So you arrange the atoms based on this principle. Sometimes you might have a challenge in determining which of the elements should be at the center. For example, in this particular case, you have nitrogen and oxygen. Which of the two? Is it the nitrogen or the oxygen that should be at the center? That you determine based on the electronegativity. So this, if you have a situation like this, you put the least electronegative atom at the middle or at the center, the least electronegative atom at the center. So we'll base, this is the first rule. So now when you try to draw the Lewis structure for NH2OH, in NH2OH we have 3 hydrogens, okay? 1 nitrogen and 1 oxygen. We know the hydrogen should be outside. So the hydrogen cannot be at the center. And so we can put hydrogen here, for example. I can put another hydrogen here and another hydrogen here. Not at the center. And then we have either nitrogen or oxygen being at the very center of the whole thing. The element that is most surrounded by others, okay? And we'll use these facts. The least electronegative atom should be at the center. Between nitrogen and oxygen, nitrogen is less electronegative than oxygen. Remember, in the periodic table, as you go across a period, the electronegativity increases. So you have carbon, next to carbon you have nitrogen, then oxygen, then fluorine. As you go from carbon to nitrogen to oxygen, fluorine, electronegativity increases. Therefore, nitrogen is more electronegative than oxygen. So the nitrogen will be at the center. So we can put the nitrogen here at the center. Of course, the oxygen, it cannot be on this side. If you put oxygen on this side, the hydrogen will be surrounded by more than 1 atom. So the oxygen can be here. Then when you look at this, the hydrogens are on the outside. The nitrogen is surrounded by not more than 3 atoms. This hydrogen, the other hydrogen, and this oxygen. Since nitrogen is trivalent, as the first approximation, it should not be surrounded by more than 3 atoms. Then if you look at the oxygen, it's surrounded by this hydrogen and by the other nitrogen by 2 atoms. As a first approximation, the oxygen should not be surrounded by more than 2 atoms. So it satisfies the requirement, okay? So now let me just copy this one, what we have established in this step. And we go, I hope we get a new slide. So this is what we have established from the first slide, the arrangement of atoms. It is very, very important you do this right. Okay? Otherwise, if you put the hydrogen in the middle, the nitrogen's on the outside, etc., it's going to be chaos. We are not going to go anywhere. Now, that's the first step. Step two is count the total number of valence electrons. You have to count the total number of valence electrons. And to know the valence electron in a particular element, you need to know its position in the periodic table. If it is in group 1, it's got 1 electron. It's group 2, 2 electrons in its valence shell. If it is a group 4 like carbon, 4 electrons. If it's a group 5 element like nitrogen, it's got 5 electrons. If it's a group 6 element like oxygen, it's got 6 electrons. If it's a group 7 element like the halogens, it's got 7 electrons. So from the position in the periodic table, you can determine and know what the valence electron is. So now, in this particular example, we have 3 hydrogens, 1 oxygen, and 1, let me write it like this, 1 oxygen and 1 nitrogen. Okay? For this, the valence electrons now, for hydrogen, of course, it is 1, so 3 times 1. 3 times 1. Total. Who is this disturbing the class A? And then oxygen, it has got, we have 1 oxygen. The valence electron for oxygen is 6. It has got 6 electrons. So in total, 1 times 6 is 6 electrons. Nitrogen, so we have 1 nitrogen, the number of electrons in the valence shell are 5. 5 electrons. So 1 times 5 is 5. So when you sum this one up, 3 plus 6, 9, 9 plus 5, 14 electrons. These are the total number of valence electrons. And these are the ones that are going to be used in forming a bond between the 3 hydrogens, the nitrogen and the oxygen. You will distribute these electrons to these elements. Then when you do so, of course, you will make sure that they have the valence electrons. I mean that if they are different, if they are elements different from hydrogen, they must have octet of electrons. If it is a hydrogen, it must have duet of electrons. So let me copy this again. And then we know total number of valence electrons we have is 14. The total number of valence electrons is 14. So now step 3, put the valence electron, the total, okay, the total, or the valence electrons, okay, let me just say the valence electrons, the valence electrons as bonding first and non-bonding electrons. So now we have this. This is how the atoms are arranged, which we determine from step 1. And then we use the 14 electrons first as bonding electrons. We use those electrons to form a bond because these 3 hydrogens, the nitrogen and the oxygen, it's a combined together. They have given us a chemical compound, isn't it? They have formed a bond with each other. So we must use these electrons to form a bond. And the bond is represented by a line, a single line like this, represent a bond. So we put a line, a line, a line, like this. Then each of this line represent 2 electrons. Okay, so now total number of valence electrons used. No, I mean, let's say number of valence electrons used, number of valence electrons used. We have formed 4 bonds. Because of these 4 bonds, we have used 8 electrons. Total number of valence electrons used is 8. The balance is 14 minus 8, 6 electrons. So when you are forming a molecule, when you are drawing the Lewis structure of a particular molecule, you must use all the electrons. We have only used 8 of the 14. We must use all of them. None of them can be left out. Now, we'll use these electrons, the remaining electrons, to fulfill the duet if it is hydrogen, and the octet if it is a period 2 element like carbon, nitrogen, oxygen, like that. So now when you look at this nitrogen, it has formed 3 bonds. One with this hydrogen, another one with that hydrogen, another one with this oxygen. Only 3 bonds. It has got only 6 electrons. So this nitrogen does not have octets. No octets. If you look at the oxygen, this one, as you can see, this oxygen has only formed 2 bonds with this nitrogen and then with the hydrogen. No octets. See? Now, we'll use these electrons, the remaining 6 electrons, to fulfill the octets of the oxygen and the nitrogen. Okay? Now, let me go, let me draw this one. Let me open a new slide. And what we have hydrogen and nitrogen, oxygen, hydrogen, and then a hydrogen. We have formed a bond with them. Each of them are bonded to each other like that. So now we have 6 electrons remaining. Okay, the 6 electrons remaining, we will use them as lone pair of electrons. So now when you do that, it is easier to fulfill first the octet of the elements on the outside. So as you can see in here, nitrogen is at the center. Oxygen is on the outside. Of course, the hydrogen is the most outside, but relatively the oxygen is on the outside. So now we fulfill the octet of this oxygen first, since it is on the outside. When you look at this oxygen, it has got only 4 electrons that come as a result of the 2 single bonds. So it needs additional 4 electrons to have octet. So you put this one here. So 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. Octet. We still have 2 electrons remaining. Now the remaining electrons, so after you have done this, if there is any electron left, fulfill the octet of the central atom. We'll look at this, the importance of this as we go along, okay? So when you do that, when you put the lone pair of electrons to fulfill the octet of the elements that do not have octet of electrons, you use the lone pair of electrons to fulfill the octet of the elements outside. And then if there is any electron left, you come and use whatever is remaining, you will dump it on the central atom, in this case on the nitrogen. Now, if you look at this, the nitrogen has got octet of electrons, octet. Of course, the hydrogens, all of them, they have duet. Hydrogen will want to be like helium, the corresponding noble gas, which has got 2 electrons in the valence shell. So all the hydrogens are duet, the nitrogen and the oxygen are octet. Then we had 14 valence electrons. We have used all of them. You can count them. Based on, because of the valence, the lone pair of electrons, 1, 2, 3, 4, 5, 6. 6 lone pair of electrons. And then the bonds are 1, 2, 3, 4. 4 bonds, 4 covalent bonds. 4 times 2, 8. 8 electrons are used in bonding. 6 electrons are used as non-bonding. 4 plus 6 is 10. So as a result, this is a valid Lewis structure 4. NH2OH. Is it okay? Do you have any question on this?
Yes.
Ikopoa, isn't it?
No.
We go and look at.
Yes, sir.
Let's look at another example, and hopefully it will be more challenging than this one. So let me first
Excuse me,
do
sir.
T. Yes.
Excuse me, sir. And what about the last step on assigning the formal charge?
You know, it's of course it is good to assign formal charge. In this case, I did not bother to assign formal charge because none of them are charged. Because you know, who is this? Who asked the question? What is your name?
Me. James.
Huh?
James.
James. So James, of course, it's very important to assign formal charges, okay? But
Yes.
you know, without calculating, I know all of them are neutral. Because I know what I know, oxygen forms 2 bonds.
2 bonds, nitrogen 3 bonds.
Yes, and then on the nitrogen I have the lone pair of electrons. On the oxygen I've got those 2 lone pair of electrons. They are satisfied, okay? Nothing, no problem at all, okay?
Okay.
That's why I did not bother, but it's very important to do that, okay?
Okay.
For practice, we still have another set of questions. Now,
Okay,
let's look at.
Excuse me, sir.
Yes.
Yeah, I also have a question. So, for example, you are told to write the, you're told to assign the formal charge, and by calculating the formal charge, you find that they are all 0. There is no formal charge. So you just leave it that way, or you have to indicate that it is 0.
No, you see, if you are told to calculate, Bwana, you have to calculate and show, isn't it?
Yeah.
Yes, it all depends on how you are asked, okay? Is this okay?
Excuse me, sir. Excuse me, sir.
Mm.
So assume it's neutral. You just leave it that way. You don't assign anything.
So let me, it is possible, okay? Let me just say this. Let me just say this from the outset, okay? I don't want you to be misled. Drawing Lewis structures, it has got 4 steps. The 4th step of drawing Lewis structure is to assign formal charges, okay? To assign formal charges. So it is important that you assign if there are any different from 0, you need to assign their charges, okay? So for example, when you're asked to draw to write a Lewis structure for a compound like this, if they are neutral, you can just leave it the way it is. I'll give you an example. For example, if we do for I, for HNO2, I know for sure the nitrogen will be positively charged, one of the oxygen will be negatively charged. So in such a case, we have to determine the formal charges and determine those ones, one of them being plus, the other one is being minus, because the charges are also part of the structure. Is it okay?
Yes.
So if you are asked for something like this, if they are neutral, you can just decide to leave it. Okay? But if you think they are charged, we can work on them. Is it okay?
Yeah.
Yes. So now let us look at the Lewis structure. Yes.
I have got a question. I was asking that should you place the charge or unless you are asked to?
You know, my dear, as I told you. Okay, let me jump this one in order to answer your question. Okay, I'll look at the Lewis structure for this one a bit later. Let me first show you the Lewis structure for this molecule. Okay, HNO2. Let me do that first. Okay, let me. Let me draw the Lewis structure for this. You remember, it is the same question as in the previous one, okay? The question says, why? The question says, where is it? Where is the question? Yeah, write a Lewis structure for each of the following, okay? The question is the same. Let's write the Lewis structure for HNO2, okay? And see what happens as we go along for HNO2. First of all, we have step 1 is to arrange, okay? Step 1 is?
Arrange the atoms.
Yes, so when you are doing this thing, marks are awarded for each of the steps, okay? Arrange the atoms, okay? The way you think you should be arranged. Now, we have hydrogen. We know hydrogen is on the outside, okay? Now we have nitrogen and oxygen. Between nitrogen and oxygen, which one should be at the very center? Nitrogen or oxygen?
Nitrogen.
Nitrogen.
Because nitrogen is less electronegative than oxygen, okay? You have nitrogen. Okay? And then the 2 oxygen, one of them here, another one here. As you can see, the hydrogen is in the outside. The nitrogen is surrounded by 3 atoms. Of course, the oxygen, as you can see, they're only surrounded by 1 atom. This oxygen is only next to the nitrogen. This oxygen is also next to the nitrogen. It does not say that they should be surrounded by the maximum number of bonds they form. It is saying, as a first approximation, when you are arranging the atoms should not be surrounded by more than the number of bonds they usually form. That's what it's saying. It is possible they can have less. It is possible they can have more. But when you attempt as a first approximation, you should not surround them by more than the number of bonds they usually form. it is an easy way to start from. Then it's only now when you have a challenge, now you can have more or less. Okay, so this is how the atoms are arranged. Now step 2 is counting the total valence electrons. Total number of valence electrons. Okay, now we have a hydrogen, one hydrogen, one nitrogen, one hydrogen, one nitrogen, and 2 oxygens. For hydrogen, it is 1 times 1. For nitrogen, it is 1 times 5. For oxygen is 2 times 6. So if you sum these ones up, it will be 12 times plus 6, 18 electrons, okay? The total number of electrons are 18. So this is how they should be around arranged. Let me copy that one. And then we have 18 electrons to distribute. Nothing more, but 18 electrons. Nothing less, nothing more. These ones you share out with this element. And as you share out, you must make sure at the end of the day, the duet rule for hydrogen and then the octet rule for the other element is followed. So the first thing you have to do is step 3 is add this or use these electrons, okay? Electrons as bonding and non-bonding electrons. Bonding means the electrons belong to both atoms that are involved in chemical bonding. Non-bonding means those electrons belong only to that particular element. So now, in here, so we use these electrons first to form a bond. So we have formed a bond between the hydrogen and the nitrogen and oxygen, the nitrogen and oxygen. Then if you look at this, the oxygens, you only see these electrons of the bond. So let me, before I do that, total electrons used, a number of electrons used. So number of electrons used so far are 6 because of the 3 bonds. 3 times 2, 6 electrons. Number of valence electrons remaining is 18 minus 6. 18 minus 6 is 12 electrons, okay? We have 12 electrons remaining. And then when you look at the nitrogen has formed only 3 bonds. It does not have octet. If you look at the oxygens have formed only 1 bond. They don't have valence, they don't have octet of electrons. So now we'll use these remaining electrons, the 12 electrons, as a lone pair of electrons first, okay? So what we'll do, we have this, and we have formed a bond like this. Now we have 12 electrons remaining. Can you tell me which one is the central atom?
Nitrogen.
Nitrogen.
The atoms that are on the outside the octet are not fulfilled are the two oxygens, okay? So we'll use these 12 electrons to fulfill. Listen to me. We'll use these 12 electrons to fulfill the octet of the elements on the outside. The elements that are on the outside are the oxygens. How many additional electron will each of them, which will each of the oxygens need to have octets?
6.
6.
Remember how many electrons we have?
6 electrons.
So we have 12 electrons. Each of them needs 6. So I put the 6. So let me use a different pen. So I have 1. So you count 1, 2, 3, 4, 5, 6 until you reach 12. Okay. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All the valence electrons are used, isn't it? We had 18 electrons, 12 of them we use them as lone pair, and 6 of them used as bonding electrons. We have used all the 18 electrons. But when you look at the nitrogen does not have octets. So.
Yes.
Now, how can we make sure the nitrogen has got octet of electrons?
By using the double bond.
By using the two electrons on either side of
By
the oxygen to
using
form a double
the
bond.
lone pair of electrons
In oxygen.
on the oxygen,
From a double
we share them with the nitrogen by forming a double bond, isn't it?
Yes. Yes.
How many oxygens do we have?
2.
So let me label the oxygens. Let me label this one as oxygen A. This one as oxygen B. Different oxygens. Ona. So now we have two possibilities of forming a double bond with the nitrogen to give the nitrogen octet of electrons, isn't it? So
Yes.
one possibility is like this. Okay?
Yes.
The other possibility is like that. Isn't it true?
Yes.
So one possibility is like this. Let me use another plain color. The other possibility is like this. So leading to two resonance structures. Did we force these two structures?
Not really.
No.
They're not forced. They came. As you see, you have followed the steps in drawing Lewis structure. So what this is telling us, when you are asked to draw the Lewis structure of a particular compound, if there are resonances, you must draw the resonances. Okay? If there are charges, you must also indicate the charges. So in this particular case, we have two possibilities. So the two possible structures are H We have the nitrogen in the middle. We can have a double bond like this. And this way, a single bond. This one is coming, if I'm not mistaken, this one is coming from A, for example, through A. The other possibility is you have H, nitrogen. This one is a single bond, while this one is a double bond. And then what I want you to see also, on both oxygens, we had 6 electrons, that as 6 non-bonding electrons, okay? So when you use 2 of them, if you use 2 of them to form a double bond, you will be left with 2 pair, okay? So on this one, we'll have these 2 pairs, the one that has formed a double bond. On this other one, we'll also have 2 pairs. But the other oxygens that have not formed a double bond, for example, if we had used this one to form a double bond, this one will have left 6 electrons. So each of them will have 6 electrons. Okay. Of course, these are resonance structures. You have to use this double-sided arrow, and then you have to draw their structures in a square bracket like this to say that none of these are real. The actual structure is the hybrid of this, the average of this. Anyway, now you will notice that this oxygen, as well as these oxygens, these 2 oxygens have formed 2 bonds. 2 bonds. Just like the way they have formed 2 bonds in water. Oxygen forming a bond with 2 hydrogens in water. In this case, the oxygens have formed 2 bonds with the nitrogen, this time with a double bond, okay? So if you calculate the formal charge on those oxygens, for sure, it will be 0. So the formal charge you can calculate, but I will visit this later when I will show you how to calculate formal charge. But you should also know that the formal charge on this oxygen is 0, and the formal charge on this particular oxygen is 0. But if you look at the nitrogen, in both cases, the nitrogens have formed how many bonds have these nitrogens formed?
4.
4. How many bonds does nitrogen form usually?
3.
It has formed more than 3. Since it has formed more than the number of bonds it usually forms, it becomes positively charged. You can calculate the formal charge on that, you'll find it is positive. This one is also positive 1. If you look at this oxygen has formed how many bonds? As well as this other oxygen. If you look at this oxygen, as well as this oxygen, how many bonds have they formed?
4. Only 1.
Number of bonds they have formed is 1. With the nitrogen. How many bonds does oxygen usually form?
2.
This one has formed less than the number of bonds it usually forms. So it will be negative. So if you can calculate the formal charges, you'll find like this. Now, this is a complete Lewis structure for HNO2. Okay? This is the Lewis structure. Not this one, but written like this. If you wish, you can write the hybrid, okay? So the hybrid, what we know, drawing the hybrid, you should not also be worked up, okay? It's very straightforward. What we know for sure, for certain, we have a bond between hydrogen and nitrogen. Isn't it true? A bond between hydrogen and nitrogen on both cases. What is also true, the nitrogen has bonded to oxygen. This is also true through a single bond. This is true. What is now not fixed? What is different in one case, in resonance A, so these are the two resonance A and B. In resonance A, we had a double bond here, a nitrogen-oxygen double bond. The same bond, this one, which was a double bond in this case, which was a double bond, in this particular case is a single bond. Then if you look at this one, which was a single bond, in this other case it is a double bond. So what this is telling us, the nitrogen-oxygen bonds are neither a single bond, but nor a double bond, but a hybrid between a double bond and a single bond. Because as we have seen, each of the nitrogen-oxygen bonds of HNO2 have a potential to be a double bond. There are also single bonds, an intermediate between a double bond and a single bond. Now, to show that, you use a dashed bond like this. So to show this is, we are saying this bond between the nitrogen-oxygen bond is neither a double bond, neither a single bond, but intermediate between a double bond and a single bond. But what is also constant in both cases, the nitrogen is positively charged. So this +1 you put. Now the -1 charge, at one time, the negative charge, one charge, sorry, I made a mistake in here, this one, sorry. This is not this oxygen which is negative, this one is neutral, it is this one which is -1, okay, sorry. The negative charge one, at one time, it was on this oxygen, or at another time is on the other oxygen, because the negative charge, it means, is shared equally between the two oxygens. So this will be -½ This will be also -½ You can go further ahead and put 2 lone pair of electrons on each of the oxygens, because those ones are, so if you look at this oxygen, it has got 2 lone pair of electrons. This one, it has got 2, these 2 plus additional 1. Having 2 lone pair of electrons is given in both oxygens. Okay, so you can put that one and then -½ Because of this, now the additional 2 electrons are shared equally between the 2 oxygens. Is it okay?
Yes.
Yes.
So we go ahead and learn more about this, okay, as with more and more examples. Okay? So now let me follow the series and then let's look at this one, okay? The Lewis structure for CH2NNH2. What we know in this molecule. Yes.
I was asking about the question, the structure you are doing about HNO2. So when you are told to write the Lewis structure, you are supposed to write the two of the two structures.
Yes, and then you put them, you show them how they are related to each other with a double-sided arrow. And then it's also good to put them in a square bracket. This square bracket you learn later, you know, everything in chemistry has a meaning, okay? So this square bracket, in this particular case, is representing, is showing that these two, A and B, are not real. The true structure is resonance hybrid of these ones, average of this. Okay?
Yes, so when you are told write the Lewis structure or write the Lewis structures, structure and structures is the same, it means the same question.
Yes, because you see, you remember that a resonance structure came as a result of the fact that we were unable to represent the structure of the molecule by a single Lewis structure. So drawing resonance structure, you have to follow the steps in drawing Lewis structure. And then when you are, okay, let me just say you draw the Lewis structure, for example, for HNO2. As we were drawing the Lewis structure, we reached a point where we have possibilities. So resonance came in. So in several examples, there will be no resonance. You will only have one fixed structure. That one, you don't need to show the resonance, because when you are drawing the Lewis structure, you are drawing the actual true structure of the molecule. And then none of the ones indicated by A or B are the true structure. So you have to show that, okay?
Yes, thank you.
Yes. Now, let's look at another example, CH2NNH2. Of course, first, step one is to arrange the atoms, okay? Step one. I don't want you to do funny things, okay? You learn very well if you follow steps, okay? Arrange the atoms. Okay, so to arrange the atoms, you know what to do. And now we have the hydrogens are in the outside. So in this particular case, we have CH2, N, and then NH2. Even the way they are arranged, it is almost indicated. So we have a carbon, we have a nitrogen, and then we have another nitrogen. On this carbon, we have two hydrogens. And then on this, the other hydrogen, we have nitrogen. On the other hydrogen, we have two hydrogens. Okay. Now, let's just look at it. You know, the hydrogens are, I was not supposed to have written this line, sorry. If you look at the hydrogens are on the outside. As you can see, the hydrogens, the way they are written, can only form one bond, isn't it? Then hydrogen forms one bond. It is okay. If you look at the carbon, by how many atoms is this carbon surrounded by?
Three.
Surrounded by how many atoms? This carbon?
Three.
Carbon normally is surrounded by how many atoms?
Four.
Now it is surrounded by less. Okay, by less. It is possible, one, there could be a charge on it. The other possibility you can imagine that because of the three bonds, it will get 6 electrons. In order to have octet, probably it has to form a double bond. In order for it to have 8 electrons. And then as you shall see later, there must be a double bond between this carbon and nitrogen. And if you look at this nitrogen again, this nitrogen is surrounded by how many atoms?
Two.
Nitrogen?
Two.
Nitrogen normally forms 3 bonds. This one is surrounded by less. It is possible that there is a double bond. Of course, there is a double bond in here. And this nitrogen, as you can see, it's surrounded by this hydrogen, and by that nitrogen, it's surrounded by 3 atoms. It has got the maximum number of bonds it can form. So you should not expect this one to have a double bond. Okay? Okay. So now, step 2 is count. I like kids, by the way, so count the total number of valence electrons. Valence electrons. So we have 3 hydrogens. Please mute, please. Where the noise from Edis is coming. it is better you mute, because when I share this one, there will be a lot of noise
So
in the
it
video.
is 4 hydrogen.
Huh?
It's 4 hydrogen.
is 4
hydrogen.
Yes, so you guys are not asleep. Okay, good. 4 hydrogens.
Excuse me.
Yes. So we have 4 hydrogens, 1 carbon, 2 nitrogens, isn't it? For the hydrogen is 4 times 1. For the carbon is 1 times 4. For the nitrogen is 2 times 5. If you add this, you will get 4 plus 18, isn't it?
18.
So we have 18 electrons to be distributed to these ones, okay?
Yes.
Okay, so let me do it. So we just put, I'm jumping the steps, okay? You know the steps. So the next one is to give them as, first to put the electrons as bonding electrons, okay?
Yes.
When you do that, how many bonds have we formed? How many bonds have we
6
formed?
bonds.
5
5
bonds.
bonds.
5 bonds.
5.
5.
But you left
5
1
bonds,
hydrogen.
meaning how many electrons?
10 electrons.
10.
Excuse me, sir.
Yes.
There's an hydrogen
The last
somewhere.
nitrogen have 2 hydrogens.
Oh, yeah.
Omitted one
Yeah, there are
hydrogen.
6 bonds.
It should be 6.
Sorry. 6. Let me write.
Then 12.
So let me write it again. What am I doing? Where is the list? Okay, so 6 bonds, meaning 12 electrons. Huh? Balance. What is the balance?
8, 6.
Balance is 6.
6 electrons.
Now tell me which element should be given its octet first?
Nitrogen.
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 Okay. The second nitrogen. So we give. So we have 6 electrons. Like that, okay? Oh, no.
Yes.
How many electrons are we left with?
4.
4. And then I can put 2 in here, isn't it? Yeah?
Yes.
And then
Yes.
now what you can see, we have octet of the carbon, isn't it? Octet.
Yeah.
The nitrogen has octet. The remaining, the balance of the electron remaining, we give it to the other element now, which does not have octets, okay? We give it to this nitrogen. Okay, now we have used all the 18 electrons. 6 of them, we use them as bonding electrons, 6 times 2, 12 electrons. And then 3 of them as lone pair, 3 times 2, 6. We have used all the 18 electrons. We have fulfilled the octet of the carbon. We have fulfilled the octet of the nitrogen on the outside. But the nitrogen in the inside, this one, does not have octets. Okay?
Yes.
How can we fulfill the octet of that nitrogen? Is the answer.
By using the valence electrons to become a
Which
bond.
particular valence electrons?
The lone pair of
The
electrons
lone
on
pairs.
On which atom? The carbon or on the nitrogen?
We
Carbon.
use the one
Carbon.
that is
Nitrogen.
carbon.
Huh?
Carbon.
I
You
think
use
we use
both.
for the ones for
Okay. Okay,
carbon.
guys.
Carbon.
Now, you see, when you have choices like this, which one will you choose? The
Okay,
one on
so
the
I
carbon
think we are
or the one on the nitrogen?
One from carbon.
okay. So I
We
think
need
we're going
one
to choose
from
the one on
carbon.
I'll
carbon
choose on the carbon.
because if we choose the one on
Choose the one for
carbon is going to have more than the number of bonds that is required.
So now, the
I
one
think
I'm going
we
to
should
use,
have
yes,
nitrogen. We should have a double bond.
Make a single bond there.
okay, I will use this lone pair of electrons to form a double bond with the nitrogen, okay? What do you think will happen if I use the lone pair of electrons on this nitrogen to form a double bond with the nitrogen? What do you think will happen?
Nitrogen will have excess number of bonds more than the
It
ones
becomes
it should form.
positively charged, isn't it?
Yes.
So if I had chosen
there is one,
the lone pair of
one,
electrons, the
two,
nitrogen, to
one,
form a
two,
double
three.
bond with this, the nitrogen will be positively charged. The whole molecule will be positively charged. But if I choose the lone pair of electrons on the carbon to form a double bond with the nitrogen, none of the atoms will be positively charged. The molecule will be neutral. Which one is more stable, the neutral or the positively charged?
The neutral.
The other result, the other one is not even a choice. So this one will not have resonance structure. The only structure that will come out of that will be, you have a carbon, double bond, nitrogen, and then the two hydrogens on this carbon, and then the nitrogen, and the two hydrogens on that nitrogen, and then lone pair of electrons on each of the nitrogens, okay? So if you look at each of the nitrogens have formed 3 bonds. Together with the lone pair of electrons, 4 times 2, 8 electrons. This one has also formed 3 bonds. So this is the valid Lewis structure for CH2 NH2. Okay? Are you guys okay?
We're okay.
Yeah, we are okay.
So let me show you the structure for this one. Okay, and then
okay, sir.
if you want after
So
that,
I have
you
a
can
question.
take me home.
So I have a question.
Yes.
Okay, which format do we use when we are assigning the non-bonded pair of electrons? Because if I may see, the first one when you are assigning the non-bonded pair of electrons in the second one, we placed the non-bonded, all of them in oxygen, the 2 oxygen. But now coming here, we place 2 on carbon and nitrogen and the other nitrogen first. So
Okay,
is there
listen,
any
I did
format
not
or
say
we
that.
just place them?
Listen, okay? Remember what I said?
Yes.
First, let's assume we have not put this one pair of electrons, okay? Let's just put them, okay? So we have 6 electrons, huh?
Yes.
So which are the 2 elements on the outside that do not have octet of electrons?
There is carbon and the other nitrogen.
Okay, now we have 6, okay?
Yes.
I can put 2 electrons on the carbon. I have 8 electrons, isn't it?
Yes.
we are left with 4 electrons, isn't it?
Yes.
Then we put these other another 2 electrons on the nitrogen on the outside. How many electrons are we left with?
I think none.
Huh?
None, because we've placed all of them.
No, you are not listening.
No, your voice is breaking, so that is the reason why.
So we have 6 electrons, okay?
Yes.
We put 2 on the carbon.
Yeah.
Another 2 on the nitrogen. This one's what we did first.
Yeah.
2 plus 2 is 4.
Yes.
But we had how many?
6.
So we have to use all the electrons. So the remaining 2 now will be on the nitrogen, okay?
Yes.
If we had nothing left, we'll not have put anything on the nitrogen, okay?
Yes.
We'll now be worried how to fulfill the octet of that nitrogen. But we had some electrons left, we can put it there.
Okay, so to mean that when we are filling the non-bonded electrons, then we start with the elements on the outer side.
Mm-hmm.
Okay, then that is the point.
On the outside, and then when you have something left, since we have to use
then
all
now
of them,
we
go to the center and we find which one needs electrons to have octet of electrons, and then give those electrons to that element.
Okay.
Okay, good. Thank you so much for the question. So now let's look at this one, okay? H, N, and H, okay? Of course, the way they are arranged is the way they are written. So we have a hydrogen. So I will jump steps. We have a hydrogen. We have a nitrogen. And the nitrogen.
Yes.
Yes. A question? So we have 2 hydrogens and 2 nitrogens, okay? 2 electrons because of the hydrogens and 10 electrons because of the 2 nitrogens. In total, how many electrons do we have?
12.
12.
Now we use these ones. Okay. How many we used? So we used 3 bonds. Three bonds, which implies 6 electrons, okay?
14, not 12.
Huh? Why are you saying 14?
4 bonds.
We have 2 hydrogens and 2 nitrogens. 2 times 1, 2. 2 times 5, 10. 10 plus 2, 12. We have 3 bonds, and to 3 bonds, 6 electrons. The balance? 6 electrons, okay? Now, this balance electron, the 6, we are going to give them to the nitrogens, okay? The hydrogens are satisfied, isn't it? Yes. Even though the hydrogens are on the outside, do they need additional electrons? No, isn't it? So now we give these 6 electrons to the 2 nitrogens. So, okay, as a pair. So I can put 2 here. 1, 2, 3, 4, and then the remaining 2 here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All 12 electrons are used, but this one does not have octet of electrons. No octet. So what do we need to do? We take these electrons and form a double bond with the nitrogen. Therefore, the Lewis structure, the valid Lewis structure for H, NNH is H, nitrogen, double bond nitrogen, and then a hydrogen, and then lone pair of electrons on each of them. This is a valid Lewis structure for HN2H or H2N2. Is it okay?
Yes.
Yes.
Yeah.
Yeah. And can I try one or two examples before you go? Or you are tired?
Yes.
Yes. Continue.
Can try.
Yes.
Thank you so much.
Yes.
I know you are
The
tired.
complicated one.
Even me, I'm very, very tired, by the way. I started
The
my day at
complicated one.
6. Yes, I don't know which one. No, let me do for sulfuric acid, okay?
Yes, we are.
Let me do for sulfuric acid. And then when you see as I'm solving your problem, you get the energy to continue with the class, okay? Let's do sulfuric acid. We are going to learn a lot from this
Those that have the
example, okay?
resonance structure.
First, let's do sulfuric acid. And then we'll go to resonance, okay? No problem. Sulfuric acid. Okay, first arrange the atoms. When you arrange the atoms, between the hydrogen will be on the outside. Between hydrogen, sulfur and oxygen, sulfur is least electronegative. Sulfur will be at the very center of the whole thing. So we'll have sulfur. The sulfur will be surrounded by oxygens. And then these oxygens are going to be bonded to hydrogen. Remember, sulfuric acid is an acid, something that gives hydrogen. So it has got 2 hydrogens that it can give, and those 2 hydrogens are on an oxygen. And then if you look at, we have 2 hydrogens, 1 sulfur, and 4 oxygen. Because of the 2 hydrogens, these are 2 electrons. Sulfur is 6. Oxygen is also in group 6, 4 times 6. So if you count, the total number of electrons is 24 plus 8, 32. Okay? Now we use...
Excuse me, sir.
Yes. Hello? Hello?
Screen.
I'm not hearing you, my dear. Who is... I'm not hearing you at all. Unfortunately, I cannot hear.
Share your screen.
Can I? Okay, let me share again. Okay, let me share again. If that is your concern, let me do it again. Okay, I've reshared it. I hope you can see it this time. So we're looking at drawing the Lewis structure for sulfuric acid. Okay, so it will demonstrate some of the most important points we're looking at. Okay, like this. So when you look at this, we have formed 1, 2, 3, 4, 5, 6. 6 bonds. 6 bond means 12 electrons. The balance 32. The balance 32 minus 12 is, how many is that?
20
electrons. Now, which are the elements on the outside? Can you tell me?
Oxygen.
Who's
Oxygen.
oxygen? The 4 oxygens are the element on the outside whose octet is not fulfilled. Okay? So let's just put this one, this electron will need 6 this oxygen will need 6 electrons. 1, 2, 3, 4, 5, 6. This other oxygen also will need 6. 1, 2, 3, 4, 5, 6. These are 12 electrons. We're left with 8. Those electrons will be used to fulfill the octet of the oxygens. 1, 2, 3, 4, 5, 6, 7, 8. Now tell me, guys, are there any electrons that are left in here?
No.
No.
We are used
No,
on the
no. They are
electrons,
all
is it?
used. Yes.
Is this a Valley-Lewis structure for sulfuric acid?
No.
No.
Why?
No, no,
Why?
no.
Because
We have not followed the octet rule.
For which one?
And
Which one?
sulfuric acid can also form resonance.
Is this a Levalier structure for H2SO4? So if you look at it, how many electrons do you see on the sulfur?
8.
Huh?
8.
Jaffa,
8.
that is 8.
8.
On the oxygens, this oxygen, which is the same as this other oxygen?
8.
8. 8.
How about this oxygen?
8.
8.
8.
Is there any element in here that does not have octets of electrons?
No.
They are all filled.
No.
No. So is this a Valley-Lewis structure?
Yes.
Huh?
Yes.
Is this the structure for sulfuric acid?
No.
Yes.
Why are you saying some of you are
Yes.
saying no, others are saying yes? Now, to see that, when you look at this, you see each of the elements have octet of electrons. The hydrogens have duet. So now let me just draw this thing again and truly see if this is indeed a Valley-Lewis structure. So we have H, O, S, O, H, and then we have O, and then on this oxygen, 3 lone pair of electrons. On these ones, 2 lone pair of electrons. Let us calculate the formal charge on the sulfur, okay? So, what is the valence electrons on the sulfur? What is the number of valence electrons?
6.
6.
Minus. How many lone pair of electrons do we see on the sulfur?
0.
Plus half. How many bonding electrons do you see?
8.
8.
So this will be 6 minus 4.
Positive 2.
The charge on the sulfur is?
Positive 2.
Positive 2.
I do not have to calculate. What do you think is the charge on the oxygens?
Yeah.
Neutral. Do not have to calculate. The charge on the oxygen is?
Positive 2.
Bana.
Negative.
Hey.
Neutral.
Negative.
I think it's neutral.
You guys do a lot of gas work.
Negative.
That's -1 and this one is neutral.
0.
Negative 1 and the other one is neutral.
4.
These two are neutral, okay? I can convince you, since you refuse to be convinced. Let me convince you by charging the formal charge on this one. On this oxygen, the total number of electrons, valence electron is 6 minus the number of valence, the number of non-bonding electrons are 1, 2, 3, 4, 5, 6. Plus half. How many bonding electrons do you see? 2. Isn't it?
Yes. That is negative 1.
6 minus 7.
Negative
Okay.
1.
So what we have in here, you have a sulfur at the middle, which is positive 2. The 2 oxygens are minus 1. What is positive 2 plus minus 1 plus minus 1?
0.
You will get when you add
Zero.
positive 2 to minus 1 and to another minus 1, you get 0. This molecule sulfuric acid is neutral. It is consistent with that. But this is not the structure for sulfuric acid. If this was the structure for sulfuric acid will be as acidic as, for example, alcohol. You remember ethanol is acidic, but ethanol, we use it as a, what is it called? Nowadays we put it in our hand as a sanitizer, isn't it?
Zero.
So I mean, ethanol, we use it as a sanitizer. Does it burn us?
No.
No.
Can you use sulfuric acid as a hand sanitizer?
Never.
Never.
No.
But if the structure of sulfuric acid,
only if you don't love your hands.
but if this was if you
It is
convince
smart
me,
corrosive.
if you convince me this is the structure for sulfuric acid, I will pour it on my hand. If you convince me this is a structure for sulfuric acid, I will pour it on my hand. I know for sure it will not burn me at all. This is not the structure for sulfuric acid. One of the things, you guys, you should see, one of the reasons why this is not a valid structure, we have this separation of charges between atoms that are next to each other. This is positive, this is minus 1. Positive, negative, positive, negative. We have 3 charges, minus 1, plus 2, and another minus 1 that are next to each other, which makes this molecule to be very, very unstable, very highly reactive. Indeed, the structure of sulfuric acid is not like this. Remember what I told you. Sulfur can have an expanded octet. It is not a must that the valence electron, the total number of electrons that surround sulfur, be 8. Sulfur does not have to follow the octet rule. Sulfur can have 8 electrons. It can have 10 electrons. It can have 12 electrons around it. Expanded octet. Because sulfur is in the periodic table is just below oxygen on the 3rd shell of the valence electrons are on the 3rd shell. Then on the 3rd shell, in addition to s and p orbitals, we also have d orbitals, except that in the case of sulfur, these d orbitals are empty. So these d orbitals can be filled. As a result, sulfur, when it forms a stable molecules, in addition to completely filling, it is s and p orbitals, 2 plus 6 with 8 electrons, it can have additional electrons going into the empty d orbitals. So sulfur can have 8, it can have 10, it can have 12 electrons. When it is formed a chemical compound, it will be stable. So to cut the story short, what is going to happen? That these 2 electrons will be used to form a double bond here. These ones will also be used to form a double bond in here. Therefore, the structure of sulfuric acid, it is this one. And then, if you want, you can calculate the formal charge on the sulfur, and then you find it is 0. Formal charge on the sulfur, the total number of valence electrons is 6, minus bonding non-bonding electrons still 0, plus half. How many bonds do you see the sulfur forming? How many bonds has it formed?
6.
6 times 2, 12. Okay.
6. Yeah.
This is 6 minus 6, 0. Because 12 divided by 2 is 6. 6 plus 0 is 0. 6 minus 6 is 0. This sulfur is neutral. All the oxygens are neutral. This is the correct structure of sulfuric acid. This sulfuric acid, I can assure you, I will not pour it, I will not put it in my hand. I will handle it with utmost care. Okay? Okay.
Excuse me, sir.
Yes.
And what can you say about the stability of that structure?
Very, very stable.
So that means it is not reactive.
Huh?
Does that mean it is not reactive?
Ahmed, you are saying?
Does that means that that structure is not, I mean, reactive?
Yes, this one. You see, the reason why sulfuric acid is acidic, is if a base comes, take away this hydrogen. Okay? If the base comes, take this hydrogen. On this oxygen, we will have a negative charge. Okay? And then that negative charge on the oxygen, through resonance, it will go to this oxygen as well as the other oxygen. It will be shared by the other 2 oxygen. So it will be resonance stabilized. I'm not going to go into the details of this because you are going to learn such chemistry later. But sulfuric acid, the reason why it is acidic, if you take away the hydrogen, it will leave a negative charge on the oxygen. And then that negative charge on the oxygen, through resonance, it will go to the other 2 oxygens that are involved in a double bond. So it will be a resonance stabilized ion. That's why sulfuric acid is very strong acid. But this is the chemistry for another day.
Excuse me, sir.
Yes.
While writing Lewis structure, must you follow all the steps? Must you just show all the steps, or just go to the answer direct?
If you go to the answer, Eric, have you ever seen big X's in your life? I'll give you the biggest X, because you must know, you must follow the steps, you must show how it is done. Okay? How you arrived at it, you must show step by step. Step 1, step 2, step 3, step 4, like that. Okay?
Yeah.
Yeah.
Excuse
I can
me,
assure
sir.
you, if you just jump and show me this is the Lewis structure for sulfuric acid, I'll just say, from where did you bring it? I'll just put a very big question mark and follow that one with a 0. Another question? Who was asking question? A
Excuse
lady?
me, sir.
Yes, Kerubo.
Excuse me, sir. Yes, I was asking, must the compound be having a formal charge of 0 for it to be approved as acidic?
As?
Must a compound be having a formal charge of 0 for it to be acidic?
No.
So
No.
then I was having a certain kind of confusion between the first and the second compound that you drew.
You see,
The first
Kerubo,
one,
you are the one who was asking, isn't it, this question, huh?
yes.
Who's asking, is this Penina or Kerubo? What happened? Okay. So now I want you to look at this. Okay. Remember, I told you if this was the Lewis structure for sulfuric acid, it will not be an acid. The reason why I'm saying this is that when if a base comes and take away this hydrogen, we'll have a negative charge on this oxygen, okay? On this oxygen. And then this oxygen, either this oxygen or this oxygen, if the hydrogen is taken away, either of them can be negatively charged. But these negatively charged oxygens are not bonded to something, are not conjugated to something with a double bond. As a result, the negative charge will be localized and remain on the oxygen. But when you look at, for this one, if you take away the hydrogen, you will have a negative charge on the oxygen. Okay, that negative charge on that oxygen, since it is conjugated with something with a double bond, the negative charge through resonance, it will come to this oxygen as well as to the other oxygen. The negative charge will be shared by 3 oxygens. So the net negative charge on the oxygen will be only -1/3. But if the structure was the first one, the negative charge on that oxygen will be -1. The first one, the oxygen will be fully negatively charged. In the second one, the oxygen will be having a -3rd charge. So the first one will be fully negatively charged. It will be very difficult for it to form, because it will be forming something that's very, very unstable. In the second case, it will be forming an oxygen through resonance that will have only a -3rd charge. So that one can easily form. It will be very stable. So it's got nothing with having a formal charge of 0 or plus something in order for it to be acidic. It's just the resonance stabilization that will come as a result of a base taking away that hydrogen, okay? But I want you guys to think about this, okay? I want you to be disturbed tonight, even maybe tomorrow, why you have these 2 structures we have seen for sulfuric acid. If the structure of sulfuric acid was the first one, it will be as acidic maybe as alcohol, okay? But why it makes sulfuric acid to be strong is because of the second structure, because the second structure, it is structure. Remember, all the time I tell you, structure determines property. The reason why sulfuric acid is a strong acid is because of its structure. So take away the hydrogen of sulfuric acid with a base. Let a base comes like -OH and take away that hydrogen. When the base take away that hydrogen, on that oxygen, we'll have 3 lone pair of electrons. The 2 lone pair of electrons that are already there, but when the OH took the hydrogen away, it left the oxygen, the electrons of the oxygen hydrogen bond on the oxygen. So the oxygen will have 6 electrons. As a result, it will be negatively charged. That oxygen, after the hydrogen is taken away, it will be -1. Both of them will be -1. The first one, it will not be resonance stabilized, while the second one, it will be resonance stabilized. Okay? So now, guys, I want to stop